Let's dive straight into this explainer. If you've ever stared at a massive, messy spreadsheet of historical data and thought, okay, how do I actually make mathematical sense of where this is going next? Well, you are in the exact right place. Today, we're going to unpack the specific data science techniques used to do just that.
Think about running a complex supply chain. You've got raw materials flowing in, finished products shipping out. What if you could mathematically predict the future of that business? Predicting those future values mathematically can literally stop incredibly costly errors from rippling down your entire operation. Look, we aren't talking about crystal balls here. We're talking about structured, statistical modeling that takes historical chaos and turns it into predictable, actionable foresight.
Here's how we're going to break it down today. 1. Why forecast time series? 2. The mathematical foundations. 3. Unpacking the ARIMA model. 4. The magic numbers, P, D, Q. And 5. Validation and advanced models.
All right, let's jump right into Section 1, Why Forecast Time Series.
A time series is really just a sequence where a metric is recorded over regular time intervals. But what's absolutely fascinating here is the sheer scale of frequency we deal with. I mean, we're talking ranging all the way from yearly annual budgets and quarterly expenses down to monthly air traffic and weekly sales quantities. And it gets way more granular than that. Daily weather, hourly stock prices, minute-by-minute inbound calls at a call center, all the way down to second-by-second web traffic. The interval itself changes, sure, but that sequential nature, that remains exactly the same.
And the crucial takeaway here is that accurate forecasts hold tremendous commercial value. Think about a manufacturing business, for instance. Forecasting your demand and sales acts as a macro solution to save serious money. It drives your fundamental business planning, your procurement, your production, because if your forecast is wrong, that error just cascades through the entire supply chain. Getting it right is absolutely critical to a company's success. Moving right along to Section 2, the mathematical foundations. Let's decode some of that heavy statistical jargon.
First up, we have the stochastic process. Now, I know that sounds a bit intimidating, but it simply represents a system that evolves over time with some level of inherent randomness built in, like tracking the daily closing price of a stock. It's essentially the underlying math for how random variables shift and change sequentially.
Next is the random walk. And honestly, this is exactly what it sounds like. It's a mathematical formalization of a path consisting of a succession of random steps. Think of it like a wandering ant. Just because you know exactly where the ant is right now doesn't mean you can guarantee where its next step will land. It's a fundamental building block for understanding how time series move.
Finally, we've got IID, which stands for independently and identically distributed. When we build these models, our ultimate goal is to capture all the underlying patterns in the data. If the leftover errors, what we call the residuals, are IID with a zero mean and constant variance, it means there's no predictable pattern left over. We've successfully isolated the random noise. We found the signal.
All right, let's get into the core machinery. Section 3, Unpacking the ARIMA model. Enter the ARIMA model. Now, ARIMA stands for Autoregressive Integrated Moving Average. It sounds like a total mouthful, but the concept is highly elegant. It's simply a tool that uses a time series' own past values to predict where it's going next. You are essentially mining your very own historical data for clues about the future.
To really wrap our heads around ARIMA, we have to split it into its component parts. On one side, we have AR, or autoregressive models. These look strictly at past values of the series to predict future ones. On the other side, we have MA, or moving average models, which take a totally different approach. They use past forecast errors to predict future values. Combine them together, and you get a highly robust predictive engine.
Okay, Section 4, the magic numbers, P, D, Q. Let's talk about the exact parameters a data scientist uses to make this thing run. If you were going to build this model from scratch, here is the exact chronological workflow you would follow. Step 1, you find the order of differencing, which we call D. Step 2, you find the order of the AR term, P. And step 3, you find the order of the MA term, Q. Let's quickly break down what each of these letters actually does for us.
The first magic letter is P. This stands for the order of the autoregressive term. Essentially, P tells us how many lags, meaning past observations, we need to use as predictors in our model. So if P is 2, we're using the 2 previous time steps to predict our current one. Simple enough, right?
Next up is D, the order of differencing. We use this parameter to make sure our time series is stationary. Stationarity just means the statistical properties of the series aren't changing over time. By subtracting the previous observation from the current observation, which is literally what differencing is, we stabilize the data. We're stripping out trends to make it flat and predictable. Your goal here is to find the exact right number for D, so your series is neither underdifferenced nor overdifferenced.
Finally, we have Q, the order of the moving average term. This represents the number of lagged forecast errors that should go into our ARIMA model. By checking those past errors, the model essentially self-corrects and smooths out the predictions. It's a brilliant little self-adjusting mechanism. Which brings us to our final section, Section 5, Validation and Advanced Models.
Because let's be real, you don't just build a statistical model and blindly trust it. You absolutely have to find the optimal model using accuracy metrics and visual tools like residual plots. You can manually validate your model using out-of-time cross-validation, which is a great way to test how well your model predicts totally unseen data. Or if you prefer, modern programming languages like Python allow you to build an auto-ARIMA model, which basically does the heavy lifting and automatically searches for the best P, D, and Q parameters for you.
And of course, as your data gets more complex, your models can adapt right along with it. You might start with the base ARIMA model utilizing past values. But what if your business has massive sales spikes every single December? Well, then you'd advance to SARIMA, which specifically accounts for repeating seasonal trends. And if you have outside factors driving the data, say marketing spend or a specific holiday, you can upgrade to SARIMX, which brilliantly incorporates exogenous or outside variables alongside those past values.
Forecasting is an incredibly powerful capability that turns looking backward into stepping forward with absolute confidence. So, armed with an understanding of stochastic processes, random walks, and the inner mechanics of the ARIMA model, what part of your business's future are you going to decode next? Think about the sequential data you interact with every single day. These models might just reveal the future hiding right there within it.